Hi there, my name is Justin Rickert, and this semester I worked on using machine learning to detect COVID-19 in chest CT scans. Our two main goals this semester were really first to just simply develop a working convolutional neural network that could make accurate predictions on these chest CT scans. And then once we got that up and running, our second goal was to run experiments on the hyperparameters of the model and see if we could either squeak out some extra accuracy or maybe find some interesting insights in how the model works as a whole. How this presentation is going to work is we're first going to go over all the background information that you would need to understand what we're trying to do here. We'll go over supervised learning, which really is the main genre of machine learning that we're dealing with here. We'll go over dense neural networks, which is the final classifier at the end of our model that determines what the model will predict. And finally, with the background information, we'll talk about convolutional neural networks, which really are really good at extracting information out of images. Next, we'll go over our methodology, how we built our model. We'll go over some of the experiments that we ran on the model that we created, and then we'll go over some of our findings and our future work. All right, so for the background information, we're going to start with supervised learning. And again, supervised learning is just the overall genre of machine learning that we're working in. Any algorithm that iterates over a large data set, makes predictions on those data set, and learns from each misprediction that it makes is a supervised learning algorithm. And the beautiful thing about supervised learning is that no pre-existing knowledge outside of the data set that you're training on is needed. So, for example, you don't need any understanding of what a CT scan image looks like, what COVID in a CT scan image looks like. All you need is the data set and a model that can learn by iterating over it. And these are just two examples out of the data set that we used. On the left, there's an image of a normal CT scan, and on the right, there's an image of a CT scan of a COVID-infected patient. Now, me looking at these two images, I don't have the slightest clue what the difference is. But as the model iterates over all of these different images that are labeled normal or COVID, it will eventually get better and better and better at making these predictions until the hope is that it will become accurate enough to be used in the medical field. So more specifically, let's talk about how our model works. And again, we use a convolutional neural network, or just CNN. So here you can see a very high level view of what a CNN would look like. You start with an input image, and that image is then passed through a hierarchy of convolutional and downsampling layers. And this is used to extract the important features out of the image. The final layer then outputs a feature map into a fully connected dense neural network. And that neural network is what makes the final prediction on the image. So now we're going to talk about each of those pieces a little more in depth, starting with the dense neural network. Now, dense neural networks are actually modeled after how our brain works. So our brain is composed of a massive number of interconnected neurons. And when one neuron fires, it sends a signal to thousands of other neurons. And if one of those other neurons gets a strong enough signal, then it will fire and send a signal to thousands of other neurons. And our brain is essentially just an interconnected web of these neurons firing. Now, of course, we want to replicate that behavior in machine learning. And we do that using dense neural networks. These are essentially made up of layers of nodes. And each node in a layer is connected to all of the nodes in a previous layer. And each of these connections between two nodes is given a weight value. Now, these weight values are really the main parameter in dense neural networks. If you have perfectly optimized weights, then your network should be extremely accurate. To determine an input value for a node, you essentially take all of the output values of the nodes in the previous layer and multiply that by their weights. To get the output value of a node, you essentially just take the input value and pass that through an activation function. There are a lot of choices for activation functions, and we'll experiment with a few later. Now, these output values feed forward through the network until you get to the output layer. And at the output layer, each node represents a prediction. Here we have two green output nodes that you can see, and one could represent COVID and one could represent a normal. Now, essentially, whichever output node has the highest output value is just the ultimate prediction in this network. Now, as we're training the model, if a misprediction occurs, then we want to backpropagate the errors. And what that essentially means is we go through all of the weights in the network and we slightly alter them to be closer to the overall output value that we wanted. And we do that using the backpropagation function. Now, of course, the dense neural network is really just the final piece in our overall CNN architecture. We still need to extract out the important features from our base input image before making our final prediction. And really, if you think about it, this is fairly similar to how our visual cortex works. Somehow, when our brain is processing visual information, it uses the features that it sees to make predictions on what we are actually looking at. So, for example, my brain is able to distinguish between two faces and determine which one is my dad. One of the most easy features to base this prediction off of would be whether he has a beautiful mustache. If he does, that's my dad. But if they both have a mustache, my brain might use more subtle features of my dad's face to distinguish who is who. And that is the goal with our convolutional and pooling layers. We want to extract out these features and we want to condense them to make predictions as easy as possible. And the first layer that we use to do this is convolutional layers. Now, these layers are made up of a series of filters called a kernel. And the way that this works is each filter traverses all of the source pixels in the source image and calculates out a new destination image based off of those values. And that calculation is made by taking the dot product of the source pixels that the filter is looking at that point and the values inside of the filter. Now, the values in the filter are trained over time, similarly to how the weights in a dense neural network are. And those values really determine what feature is being extracted by that filter. Now, the kernel is made up of multiple filters, which means that multiple features can be extracted in each layer. And that output is called a feature map. And the magic really starts to happen when you stack these feature map and convolutional layers on top of each other. You can really extract very high level features when doing this. For example, the first layer might extract something very simple, such as there's an edge between these two objects. But with multiple layers, the final layer might extract something very high level, such as this image contains a face. Or even more specifically, this image contains a beautiful mustache. So yes, that is one of the main layers in the hierarchy in a CNN. The other main layer is pooling layers. The overall purpose of these layers is to downsample the resolution of the original feature map. And the purpose of this is to make feature extraction down the line much easier in future convolutional layers, and to ultimately make the prediction easier to make in the dense neural network. Now, these layers split the input feature into 2x2 grids, and essentially simply just take the maximum value in each of those 2x2 grids and output that into one destination pixel. Ultimately, that downsamples each input feature by 75% without actually losing much of the important information along the way. And now, ultimately, that is the last main piece of the overall CNN architecture. Again, the way that this works is you have a hierarchy of convolutional and pooling layers that extract the important features, and then that final feature map is then input into a dense neural network to make the final prediction on the image. Now let's go over the overall methodology and how we built and trained our own model. And as with any supervised learning algorithm, the first step is to find a good labeled data set. And we found one that consisted of 2,282 COVID chest CT scan images and 9,776 normal chest CT scan images. We then split those images into two subsets. The first being the training set. Now this is used for the overall model to train its weights. And whenever an error occurs in the training set, that error is then back propagated through the neural network. And this consisted of 4,000 images that had a 50-50 split between being normal and being COVID. We also made a validation set that consisted of 500 images that also had that 50-50 split. But any error made in the validation set was not actually backpropagated. This was made solely to track the overall accuracy of the model that we had made after going through each training set one time. Now, our model was made up of 4 main pieces. The first was very simply just a normalization layer. That takes all the pixel values in each of the input images and just converts each value to be on a scale between -1 and 1. That really just makes things easier. And next, and most importantly, we used a pre-built convolutional neural network called ResNet 50 v2. Now, the beautiful thing about using a pre-trained network like this is that training all the convolutional layers and all the kernels inside of them is very difficult and requires a large amount of data, an amount of data that we did not have. However, ResNet 50 v2 was trained on a data set called ImageNet. Now, that consists of 14 million images, all with 30,000 different classifications. Essentially, that means that ResNet 50 v2 is already fantastic at extracting the features that we need. All we need to do is cut off the dense neural network classifier that was built in and replace that with our own, which is what we did. So ultimately, we never had to worry about training our own convolutional layers. ResNet 50 v2 was already pre-built to extract all those features for us, and it did a fantastic job. After ResNet 50 v2 output its final feature map, we then applied a global average pooling layer. That essentially takes all of the features and for each feature converts all of the pixels into one average value. That makes it very easy for the dense neural network to tell if a feature exists in that image. And of course, our final piece of our model was a dense neural network classifier, which made the final prediction on whether or not the input image contained COVID or was simply a normal CT scan image. So over the course of all of our experiments, we trained each model in a very similar way. So first off, each model went through exactly 100 epochs. That essentially means that the model iterated over all of the images in the training set 100 times. And this process generally took about 1.5 hours on my personal machine. And on that machine, we used a Threadripper 3960X CPU, we used an RTX 2070 Super GPU, and we used 128 gigabytes of DDR4 RAM. Alright, now on to some of the experiments that we ran. And remember, because we used ResNet 50 v2 to handle all the convolutional and pooling layers, we really could only experiment with the hyperparameters dealing with how the dense neural network operates. Now, our first experiment was on activation functions, and if you remember, the activation function is essentially the last little bit of computation that determines the actual output of each node in a dense neural network. And we first compared the linear and the softmax activation functions. The linear activation function essentially does no additional computation, whereas softmax takes all of the output values and normalizes them onto a probability distribution between 0 and 1. And as you can see with our experiments, these are the two best models that we had with both activation functions. And both of these models maxed out with a max validation accuracy of 94%. And also the graphs over time as the epochs continued look very similar. So really we didn't see much of a difference between these two activation functions, which makes sense. Softmax really only becomes valuable when you have more than 2 classifications that are possible. And in our problem, we only have 2, normal or COVID. Now, 2 more activation functions that we experimented with were ReLU and leaky ReLU. Now, ReLU operates very similarly to the linear activation function, with the main difference being that ReLU's absolute minimum output value is 0. Now, this can actually have some massive implications if the neural network initializes with a strong negative bias in its weights. This would essentially mean that all of the output nodes have an input value that is negative, which would then cause the output value to always be exactly 0. Now, there are 2 main issues that this can cause. The first being that the network is essentially unable to learn. The backpropagation function completely fails to update the weights when the output value is 0, which would essentially mean that this network would be stuck with this negative bias for forever, no matter how long you train. The second issue is that making an intelligent classification is essentially impossible if all the output nodes have the exact same value. And in our run with ReLU, we came across this case a couple times. Essentially, it appears that our model made the exact same prediction every single time, no matter what image it was presented with. And that is evidence of our max validation accuracy of 50%. If you remember, our validation set has a 50-50 split between COVID and normal, which supports this claim. Now, the leaky ReLU activation function solves a lot of these issues by adding a slight gradient in the negative range, essentially causing all negative values to not actually output a output value of 0. And when in our experiments with this leaky ReLU activation function, we came across very similar accuracy and graph outputs as in linear and softmax, with a max validation accuracy of 94%. So ultimately, in conclusion, it seems like the activation function doesn't really matter that much in our problem. Between linear, softmax, and leaky ReLU, the graphs are all very similar and the accuracies are all very similar. So really any choice would be sufficient in our overall network. Now finally, we experimented with the learning rate in our neural network. Now the learning rate is just a parameter in the backpropagation function. It essentially determines how drastically the weight changes whenever an error is found in the training set. Now there are a couple of issues that you want to avoid with the learning rate. The first being, if the learning rate is too high, we often see the accuracy in the overall model over the course of several epochs change extremely drastically. And also in the later epochs, you generally find that the weights cannot become perfectly nuanced and thus cannot become perfectly accurate. On the flip side, with an extremely low learning rate, we find that in the early epochs, the accuracy generally slowly increases over time, but eventually plateaus and is also unable to perfectly optimize its weights. So ultimately, the goal is to find the perfect Goldilocks between the two. Not too stable, but not too erratic. In our experiments, the two most accurate learning rates that we experimented with were 0.01 and 0.001. Now, when looking at the graphs, you can see that 0.01 is still a little too erratic for our liking. You can see that there are a ton of spikes over the course of dozens of epochs. Now, with 0.001, you can see that the overall accuracy is fairly stably increasing. You don't see many spikes at all, and really the accuracy in total is very comparable to 0.01. So ultimately, we decided to go with 0.001 because it had the extra stability and was pretty much as accurate as all the other experiments. And I will note that in other experiments where we had a learning rate of 0.001, we did find an accuracy of 94%. So overall, that seemed to be a good choice. So last but not least, on to our findings and future work. So ultimately, our absolute most accurate model used a learning rate of 0.001, an activation function of leaky ReLU, and was trained for 100 epochs. And this model maxed out at a validation accuracy of 94.4%, which really is just absolutely fantastic. When I first started this project, I was hoping to hit somewhere around 95%, and I am very happy with creating a model that is this accurate. Moving forward, the project is definitely not done at this point. We definitely need to implement a test set as well. This would allow us to make predictions on a third and final set of data that isn't perfectly 50-50 split like what we're dealing with right now, and that would help us get a better gauge on where this model breaks down right now, whether or not it produces more false positives or false negatives and other analytics like that. And we'd also like to consider implementing a feature pyramid network instead of a convolutional neural network. A feature pyramid network is very similar to a CNN, except that it makes multiple predictions after each convolutional layer rather than making one prediction after the final convolutional layer. And yeah, ultimately that's been our project. Thank you very much for watching, and let me know if you have any questions.